Hello and welcome to this episode of Night Sky News for November 2024 with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about what you can see in the night sky in the next few weeks, and then we chat about what's been happening in space news in the past few weeks. In this episode, we're chatting all about whether there are primordial black holes passing through our solar system, plus the stats on the latest round of observing proposals to use the James Webb Space Telescope, and whether black holes could be dark energy and responsible for the accelerated expansion of the universe. There's chapter markers down here if you want to skip ahead to any specific news story, and any research articles I mention are all going to be linked in the video description down below, free to read. So without any further ado, let's kick things off and start by looking up. All right, we've got a really nice setup for seeing the naked eye planets wherever you are in the world in the next few weeks. With Venus in the west setting just after sunset at the same time as Jupiter rises in the east, with the slightly fainter yellowish Saturn in between in the south. The reddish Mars then rises a few hours later behind Jupiter. So if you've got a few hours just after sunset to keep an eye on the sky, it's a really fun time to get out there at the minute if it's clear. Now, the very bright Venus is hanging around the Teapot of the constellation of Sagittarius at the minute. So that's not like an official part of the constellation. It's just a few stars that are very bright in the constellation that make this shape of roughly a teapot, and once it's been pointed out to you, you can't unsee it. The direction of the center of the Milky Way is also in Sagittarius as well, so it's a fun thing to be able to point to in the sky. It's where there's lots of stars and dust as well that you can sort of see structure in from really dark sky sites. This is going to be easier to spot the further south you are though, because Venus is still fairly close to the sun, so it's not getting that high above the horizon for those of us further north. But throughout the end of November and December, it is going to be moving further along its orbit around the sun, which means it will be rising higher and higher as we get into December. Now, if you're not sure what you're looking at is definitely Venus, then the crescent moon is actually going to sweep past Venus on the nights of the 4th and 5th of December to help mark the way for you. It will then keep moving through the sky so that by the 7th and 8th of December, it's closer to Saturn, again, helping you spot Saturn, which is quite a lot fainter than Venus and can blend a bit more with the background stars. And if you have a run of clear nights through December, notice how Venus and Saturn are actually getting closer and closer together from our perspective here on Earth, in time for their closest approach on the sky in January, which will be something nice to look forward to after Christmas, but more on that in next month's episode. And on the 7th of December is also when you should try and spot Jupiter, as it reaches what's known as opposition. So it'll be on the exact opposite side of the sky from the sun, a full 180 degrees in the other direction, meaning the sun, Earth and Jupiter are all in a line, which means Jupiter will be perfectly lit from our perspective here on Earth, and it's the brightest it gets in the sky. Every time Jupiter reaches opposition, it always takes me off guard and surprises me how bright it actually gets. Especially when it's sort of rising in the east, with the sort of dark evenings we have in the winter here in the northern hemisphere as well. And it's really low in the sky. Sometimes my brain almost tries to convince me that there must be a hill over there with a house on it, or a car that's driving along the road and it must be car headlights because it's so incredibly bright. Honestly, this is something that you really should try and get out and see, because it is just a wow moment to see how bright Jupiter can actually get. Don't worry though if it is cloudy on the 7th of December, because this is going to look really bright in sort of the week either side of that as well. So again, if you're not sure where exactly to look, by the 13th of December the moon will be close to full and getting close to the bright Jupiter, which, as we talked about last month, is still inside what's known as the winter hexagon of the 6 brightest stars around Orion. The moon and Jupiter will also be close to the Pleiades star cluster, always a fun one to look at through binoculars or a telescope, because it looks kind of like a mini plow or mini Big Dipper, whatever you call it. But because the moon will be so bright when it's full, you might want to sort of spot, where the Pleiades is when the moon is close, but then come back a few nights later once the moon is shifted, so that you can really get a full appreciation for what it looks like through binoculars. Perhaps maybe wait till see if it's clear on the 17th or 18th of December, when the moon will have moved to be closest to the reddish Mars on the edge of the winter hexagon lower in the sky. Now, the incredibly annoying thing about the moon being nearly full on the night of the 13th of December is that this year, that night is the peak of the Geminids Meteor Shower, which is objectively one of, if not the best meteor shower of the year, which is visible wherever you are in the world. In a typical year on the peak, you can see anywhere from 100 to 150 meteors per hour. That means you typically see 1 to 2 shooting stars per minute, at least in the darkest of skies away from light pollution. And therein lies the problem, because the full moon is pretty much an astronomer's worst nightmare. It is like a natural source of light pollution that can be just as bad as, the bright lights of the city for washing out, all but the brightest of stars, and in this case, the brightest of meteors. Which means that the Geminids won't be as spectacular as in previous years. They're really known for being like slower moving meteors, which is why it's just kind of like a joy to watch them. You might see a few more in the nights before the peak, so from around about the 7th of December running up to the 13th when the moon is less bright. But obviously there won't be as many meteors streaking across the sky as there would have been on the night of the peak. If you do want to try and make a night of this though and see if you can spot some Geminids, then the best time to actually view this would be after midnight, when the radiant in Gemini, the part of the sky that all the meteors appear to shoot away from, is higher in the sky, so you will lose less over the horizon. You will still see some meteors, if you go out early evening or early morning, but again, you're going to see less of them because you're going to lose them over the horizon. Best thing to do, lie flat on the ground and just look directly up. That gives you the best perspective on the biggest area of sky, so again, you're going to spot more shooting stars, hopefully. If you do decide to make a night of it and you're in the northern hemisphere, then please do wrap up warm. We are steadily approaching the start of winter, with the winter solstice coming on the 21st of December, and it can get really cold, especially on clear nights. This is why I said objectively the Geminids is the best meteor shower. Personally, my favourite is the Perseids meteor shower that happens in August each year, because usually that means I can go out at midnight and it's still fairly warm compared to the Geminids that happens in mid-December. Speaking of meteor showers, did you see this news story a few months ago about how NASA's DART mission may have created a brand new human-made meteor shower from the debris thrown up when it impacted with the asteroid Dimorphos back in 2022? Now, when you see a headline like that, I'm sure, like me, you cannot help but get excited about how cool this thing would be to see in the sky for yourself and just basking in how amazing space is. But like with any news on the internet, you have to question the source that this news came from, and make sure that the one article that you've read hasn't overhyped something by cross-checking with other news articles. We all know that we have to do it, but let's be honest, it sounds exhausting. That's where Ground News comes in. They're a sponsor that I've been working with for over a year now. With Ground News, I can see straight away that 47 different news stories covered this story, with 90% of those sources having high factuality ratings, something that is so crucial in science reporting. The handy summary at the top also tells me that this news story has come from a new study that's been published. So within a few quick glances, I can tell that this story is genuine, and I can get excited again about human-made meteor showers. Ground News is the brainchild of ex-NASA engineer Harleen Kaur. She created an app and website that lets me cross-check facts across sources worldwide. This ability to zoom out on a news story has been so vital this past year. Yes, of course, on science and space news coverage, but also with election news coverage in both the UK and the US that helps me get accurate coverage of the news without that emotional response that social media posts try and trigger. Which is one of the reasons I think that their best feature is definitely their blind spot feed, where you can see which stories had little to no reporting on either side of the political spectrum. So if you head to the link in the video description down below, ground.news/Dr. Becky, or you can scan the QR code up here, you'll get an increased discount of 50% off their Vantage plan, which gives you unlimited access to all of their features. It comes out at around about $5 a month. It's only available for a limited time. Plus, subscribing to Ground News directly supports my channel so I can keep making night sky news episodes. So a big thanks to Ground News for sponsoring this video. And now let's come back down to earth and chat about what's been happening in space news in the past month. Alright, the big thing on nearly every astrophysicist's mind this month was the JWST observing proposal deadline on the 16th of October. This was an open call for proposals for people to put in applications to use the James Webb Space Telescope for their science. You have to put together a big document of all the targets that you want to observe, but also a scientific justification for why it's important that your proposal gets time over others, what your observing plan is, so how you plan to take the data and why, then what your analysis plan is, what you will do with the data once you've got it. Each proposal gets sent out to a number of reviewers who review them blind, so they don't know who's written it essentially, and then the proposals get ranked by scientific merit. There's around 600 astronomers worldwide that get asked to do this each year, and it's completely voluntary. They don't get paid any extra for it. It literally just becomes part of your job for a while if you're asked to do it. The successful proposals that get chosen will be told in February 2025 and then have their observations scheduled for between July 2025 and June 2026. So this whole process is so important because this is what sets what JWST will observe, in the next year. And unsurprisingly, JWST was way oversubscribed by a factor of 9. So that total time requested of about 78,000 hours was 9 times more hours than are just physically available in a year that they can award to people. There were over 2,377 individual proposals, which was 446 more proposals than last year. Molly Peebles, who's an astronomer at the Space Telescope Science Institute in Baltimore that does the day-to-day running of the Hubble Space Telescope and JWST, has been tracking this herself for the benefit of the astro community for years. Basically, people self-report to her. They're oh, I submitted my proposal at this time and it was allocated this number in terms of the amount of proposals that have been submitted by that time. And so you can see from this graph where you've got time on the x-axis before the deadline and then the number of proposals submitted on the y-axis, that for all of basically the cycles for the Hubble Space Telescope, so a cycle being a year where they put out a call for proposals, it's been roughly the same number of proposals for around about 13 years or so. And of course you get that classic ramp up of submissions towards the deadline time on the right hand side of this plot. But for JWST, there's been more and more proposals submitted each cycle, each year, right? As astronomers just get a better handle on what JWST is capable of as more and more data is made public from the previous years of observations. It's fun to see a breakdown by topic of the proposals as well. I think it comes as no surprise that the majority of proposals were made up of those wanting to study high redshift galaxies, aka the most distant galaxies in the universe. This is, after all, what JWST was designed for. Closely followed by exoplanet atmosphere studies and the studies of nearby stars. In February, they'll also make the list of chosen proposals public as well, so we'll do a deep dive into that in the new year, seeing what JWST is going to observe, so make sure you're subscribed so you don't miss out on that. If you want to look at the proposals that were successful in previous years, cycle 3, cycle 2, and cycle 1, then I'll put a link in the video description down below so that you can have a little bit of a browse. Now for my science, I didn't put in an observing proposal to use JWST for this cycle, but I did put in an observing proposal to use the Hubble Space Telescope. A few weeks ago, the Space Telescope Science Institute announced a mid-cycle call for proposals that made a few people rather sad. They pointed out that the NASA budget was tight and they were starting the process of phasing out the use of some of the instruments on the Hubble Space Telescope, which means that in this mid-cycle call for Hubble, so usually the Hubble proposals are sort of springtime and the JWST ones are autumn time, but they're doing a mid-cycle call here, they were specifically calling for proposals that needed the instruments on board the Hubble Space Telescope, i.e. the science could not be done with another existing either space or ground-based telescope. Look, we all knew this was going to happen, right? And that one day, we wouldn't have the Hubble Space Telescope to use for astronomy anymore. But it feels like that day has come earlier because of budget constraints. It still works. It's not broken. And there's still a need for it, a massive need for it in so many different fields in astronomy. So a lot of people have been publishing papers to put down why that is in writing. So we can then use that to lobby NASA and ESA, the European Space Agency, and by extension, the US and the European governments to up the budget and to continue to fund Hubble. I know a lot of you at home will be screaming, keep the politics out of science, but it's impossible to do that when the majority of science is funded by governments and taxpayers. And for those of us in the astro community, we've all been talking in the past few weeks about the uncertainty that's been added to this whole situation by the new administration in the US. We don't know what's going to happen when they come into power in January. With Elon Musk, the main financial backer of the Republican election campaign, I think the astrophysics research community are understandably concerned about the ripple effects this will have. Will there be pressure on NASA to perhaps spend more on the space exploration side of things? For example, the Artemis program to send people back to the moon, or even going further than that and sending people to Mars, which I've talked about on this channel before. I don't think it really has the best ratio in terms of science learnt versus cost of program. If that is the case and there is that pressure to spend more money on space exploration, because that means, NASA spending more on commercial contracts with the likes of SpaceX, but the NASA budget stays the same, then that money's got to come from somewhere, and the most likely place it's going to come from is to take it away from the astrophysics budget. And so that raises questions like, is the funding for telescopes going to get cut? The likes of continuing to use Hubble and Chandra, but also like future observatories that are planned, like the Habitable Worlds Observatory, for example, which is the plan for beyond JWST. Like, could we see funding that's been earmarked for the development of Habitable Worlds Observatory diverted to more of the space exploration side of NASA? There's just so much uncertainty right now. Of course, with Musk now being offered an advisory position in the government itself, there's now a question of like, is there a conflict of interest for, any government-funded NASA programs to partner with SpaceX? Like, I don't know, but I think it's going to be very interesting to see how all this plays out. But let's just all keep our fingers crossed that it's not the, NASA astrophysics programs that are the collateral damage in all of this. All right, next up, let's talk about this study from Tran and collaborators, who have proposed using the solar system as a black hole detector, specifically for primordial black holes that could be hiding in plain sight and be an explanation for dark matter. So there's a lot of buzzwords there to unpack. Black holes, primordial, and dark matter. So let's start with black hole. That's an area of space where you've packed so much stuff that it's become so dense that the pull of gravity is so strong that not even light can escape, so we can't get any information from it and can't directly see anything from beyond what's known as the event horizon. The only way to make a black hole that we actually have observational evidence for it actually happening is during a supernova, when a star runs out of fuel for nuclear fusion and the core of the star collapses down into a black hole. There is a minimum mass for how heavy black holes can be that are formed in this way. It's called the Tolman-Oppenheimer-Volkoff limit. I talked about it on this channel before. It's around about 3-ish times heavier than the sun. If you have a star that is not as big, its core won't collapse down into a black hole, it will collapse instead down into a neutron star. And that's because in a neutron star, you've got neutrons closely packed as they can go that are resisting that crush of gravity down any further into a neutron star. It's only when you reach that limit of around about 3-ish times the mass of the sun that collapse down into a black hole will occur. But a primordial black hole, though, is a hypothetical type of black hole. So we don't have any observational evidence for this actually occurring. But what we think happens is that in the early universe, when the universe was much different to how it is today, it was much hotter and denser, you could essentially have random fluctuations that made one area of the universe ever so slightly denser than another area, and maybe even dense enough that you could get a collapse down into a black hole. But because you're just relying on chance that there's going to be some random quantum fluctuation to put enough material there to make it dense enough to have a collapse down into a black hole, you can theoretically make a black hole of any mass in that process. So it could be, around about the mass of the Earth or massive asteroid, or even smaller than that, like even just a few atoms. And there could be untold number of these primordial black holes that are left over from the early days of the universe. We just wouldn't be able to directly see them. But, people have been searching for observational evidence of their existence for decades, either through their lensing effect on background stars, or because some of them should have evaporated already due to Hawking radiation. If that happens, we should see like a big burst of gamma rays from them. But we don't have any convincing observational evidence that they exist just yet. So primordial black holes are still hypothetical. But given that the maths of what's happening in the early universe predicts that these primordial black holes should exist, people have considered whether their existence could help solve some of the unsolved mysteries left in astrophysics. For example, JWST's overmassive galaxies problem, which primordial black holes could help to explain, because it would mean that galaxies would form earlier in the universe and have more time to grow that massive as we're seeing with JWST. Or could primordial black holes help solve dark matter? So what's dark matter? Well, it is matter that we can't see because it doesn't interact with light in any way. So it doesn't interact with the electromagnetic force, but it does with gravity. So we know that it's there thanks to its gravitational effect on the things around it. As astrophysicists, we have a huge mounting pile of evidence in favor of dark matter. I've covered that in a video before if you want to check that out. But I've also covered work by my colleagues who are investigating alternative explanations to dark matter, like whether our best theory of gravity, Einstein's theory of general relativity, is actually wrong. I'll link all those videos down below for you if you want a bit more of a deep dive. But for now, we've got particle physicists that are searching for possible particles that could explain dark matter, but you've also got astrophysicists considering, okay, well, could it have been all the things that we just can't see in the universe, like gas and dust and planets and black holes? But there's just not enough of that stuff to explain the amount of dark matter that we infer is there. So people have turned to this idea of primordial black holes. Again, I've covered this idea as an explanation for dark matter in a video before that goes through the evidence for and against it. And it's worth stating that this idea of primordial black holes as dark matter is not perfect. It needs some more work because there are some observations that this hypothesis just can't explain yet. But I think the biggest stumbling block for all these ideas that consider primordial black holes, whether it's dark matter or observations of overmassive galaxies from JWST, is that we don't have any observational evidence that these primordial black holes actually exist. And that's where this paper from Tran and collaborators comes in. And they say that if primordial black holes exist, and if enough of them formed in the early universe to account for all the dark matter that we think is there, and if they're distributed, just sort of like roughly evenly spaced around the universe, then one primordial black hole should pass through the inner solar system, so inside the orbit of Mars, once every 10 years. And if this was the case, then the primordial black holes should pull on those 4 inner planets of the solar system due to its gravity and cause them to wobble relative to each other by an amount that we should be able to measure. Here's one of their models showing what a primordial black hole around the mass of an asteroid does to the distance between Earth and Mercury in the pink line, Earth and Venus in the green line, and Earth and Mars in the orange line. Note the scale on the y-axis here. This is in meters. So the effect is tiny. Now, the precise positions of the planets in the solar system are tracked to just about that accuracy, which would mean that the uncertainties on our measurements would be around about the amplitude of the changes here. So if we're actually going to try and use this method to detect a primordial black hole floofing through the solar system, our data needs to get more precise, and we need to take that precise data for, a few decades yet. So sadly, as exciting as this is, and the idea is that we could maybe find observational evidence for primordial black holes, I think we're just going to have to add this to the pile of things we can test in the next 20 years. But sticking on the topic of black holes, next up let's talk about this paper from Croker and collaborators, which claims black holes could be dark energy. Not dark matter this time, dark energy. Dark energy is just the name that we give to the thing that is causing the accelerated expansion of the universe. But again, we don't know what that is. And if this all sounds familiar, it's because this research group first published their evidence in support of this idea about 18 months ago at the beginning of 2023, and I covered it in a Night Sky News at the time. I'll link that video below for you because I went into more detail than we've got time to go into here, but I will briefly recap. Starting with what even is dark energy, well, we've known that the universe is expanding for over 100 years now. The space between galaxies is stretching so that it appears as if galaxies are moving away from us, and the further away those galaxies are, the faster they appear to be moving. Then at the end of the 90s, recent collaborators actually showed that as you look at even more and more distant galaxies, they appear to be moving away faster than predicted by just a constant rate of expansion of the universe. What that means is that space has been stretched more than expected over the time that the light from those galaxies has been traveling to us. And what you conclude is therefore that the universe's expansion rate must be accelerating to give you that extra stretch that is really only noticeable over those much larger distances or larger amount of time. What's causing that though, we don't know. Like, it has to be something acting against gravity, like gravity pulls everything in towards each other. So this must be pushing everything out in what's known as a negative pressure, like pressure pushing down on you. This is pressure pushing outwards. And we call this mysterious pressure, force, or energy dark energy. But you could literally call it anything you like. Now, there's been a number of ideas, hypotheses that have been raised over the years to explain what could be causing this accelerated expansion, what could be, dark energy. And one that's been knocking around for a while is that it could be black holes that are the cause of this accelerated expansion of the universe. And it all comes back down to the age-old question of what is beyond the event horizon of a black hole. What's inside a black hole? And the event horizon is that point of no return where you'd have to be traveling faster than the speed of light to escape it, which we don't get any information from, so we don't know what's inside it. It could be a singularity, which is what the maths predicts. All the matter is crushed down into an infinitesimally small, infinitely dense point, or it could be there's some exotic form of matter that we don't know about that resists the crush of gravity down, but that has an escape velocity greater than the speed of light, so you still get this sphere of an event horizon around it. Or it could be something known as vacuum energy resisting that crush down. This is an idea that's been around since the 60s. Vacuum energy is the energy in space-time itself, just like hanging around. If you have around about a cubic meter of space-time, then you're going to have a nanojoules worth of vacuum energy. And if black holes have vacuum energy inside the event horizon resisting that crush of gravity down, then as the universe expands, black holes will also expand, gaining more vacuum energy. And what did Einstein tell us? Energy and mass are equivalent, E equals mc squared. So as the universe expands and black holes expand and gain more energy, they also gain more mass. They grow in mass somehow, even if you haven't seen material get close enough to them. And if right now that's raising a lot of red flags at home for you, because you're like, well, what about conservation of energy? One of the fundamental rules of physics is that energy must be conserved somehow. You can't just make it out of nothing. And yes, that is correct. So if the black hole grows heavier, then space-time gets diluted, and that gives you a negative pressure pushing outwards, which could be what's causing the accelerated expansion of the universe. The technical way of putting this is to say that black holes and dark energy are cosmologically coupled. Now, back in February last year, Farah and collaborators published their evidence for this idea, suggesting that supermassive black holes seem to be getting heavier than they're predicted to from their correlations with their galaxies. Now, I did not buy that evidence, that claim at all. Supermassive black hole growth is my area of expertise, and I just don't think we understand it enough and all the processes that are at work to make that kind of statement. Like, my research is quite literally on an overlooked process inside galaxies that grow supermassive black holes that has nothing to do with dark energy. And when one of the co-authors of those two original studies, Kevin Croker, came to Oxford to give a talk on this research and present it, we actually had a really nice science chat where we sat down and discussed all of my reservations. And I actually go into those again in more detail in that original Night Sky News video if you want to check that out. And so, of course, this research team will have long been looking for different ways of finding observational evidence for this idea that's separate from what we know about how supermassive black holes grow. And so this month, this research team have published this paper by Croker and collaborators that comes at this problem from a different angle. Instead of trying to find evidence from studies of black holes, they're instead trying to find evidence from our studies of dark energy, specifically the Dark Energy Spectroscopic Instrument, or DESI, which is a survey of the positions of galaxies in the sky taken with a telescope at Kitt Peak in Arizona in the US. From the positions of galaxies at different distances, they can trace out the big structures in the universe and how they've changed over time thanks to the expansion rate of the universe. I already covered in a video the first year of their results, which were published earlier in 2024, and the very interesting thing that they found is that the amount of acceleration of the expansion of the universe was actually changing with time. According to DESI, dark energy was changing with time. And so what Croker and collaborators have done is say, okay, let's assume a model for how many stars have formed over time. And then the amount of black holes formed should then trace the amount of stars formed as well, if the only way to make a black hole is through the collapse of the core of a star in a supernova. And if that's the case, you then know, okay, how many black holes have been formed over time, and if dark energy is cosmologically coupled to black holes, we can then model, okay, what should be the behavior of dark energy over time? How should the accelerated expansion of the universe change over time? You can then compare that model to the DESI results. So that's what this figure shows here. The x-axis is time, with now on the left and the early universe on the right. The coloured shaded regions are the results from DESI, with the shading reflecting the uncertainty on their data, right? It could be somewhere in that range. And then the different colours reflect the different answers you get from using different samples of supernova to constrain the data from DESI more. So basically, the DESI results say the behaviour of dark energy should lie somewhere in those shaded regions that are plotted out here. Then the two black lines are Croker and collaborators' models saying, okay, black holes are cosmologically coupled to dark energy, it's because of vacuum energy, that whole model, right? And you've got two different assumptions about the amount of stars forming over time. The dashed line is kind of like your standard canonical model, whereas the Trinker model, shown by the solid line, is an updated model based on observations from JWST about the early universe that have shown more stars seem to form earlier. And so Croker and collaborators argue that this idea of black holes coupled to dark energy could explain the DESI results because they lie within this shaded region, except for in the last 2 billion years or so when the two start to disagree. And I think that's because not as many of the massive stars that actually collapse into black holes have been formed in that time. They're basically saying black hole production has slowed down in that time. They look at some statistical tests as well and find that their cosmologically coupled black hole model is actually a closer fit to the DESI data than your typical best model of the universe, what we call lambda CDM, which doesn't have a change to dark energy over time. And what's more is that Croker and collaborators claim that this idea of black holes as dark energy could also solve the crisis in cosmology, aka the Hubble tension, which I have covered many times on this channel before. Basically, our methods to calculate the current rate of expansion of the universe don't agree. But if you use their cosmologically coupled black hole model, then the number you get for the current rate of expansion, known as H0, is much closer to other observational measurements like the one from DESI, for example, and the recent ones using JWST data that I've talked about on this channel. Again, I'm going to link all these videos down below if you want a deep dive into this. But for those of you who've been around and following me for a while and have heard me talk about this before, you will understand why this is such a big deal that they're claiming that their model fixes this. But not only that, also explains why those two main measurements of the current rate of expansion of the universe don't agree, because one's been looking at observations from the early universe and one's been looking at observations from the nearby universe, and you'd never expect them to agree if dark energy is changing with time as more black holes are formed and grow more, as they're suggesting. So yes, this does all sound very promising for now. Personally, I still have some doubts, not least the fact that the uncertainties on the DESI observations that we have are so huge that you could pretty much claim that anything fits to this data at this point. Thankfully, there is more data from DESI coming. We've just had the first year of observations. We're going to get many more years of observations, which should help tighten those uncertainties on what DESI has found, which will allow us to more rigorously test this idea of black holes cosmologically coupled to dark energy. And who knows, maybe that data will finally convince me. Alright, that's it for Night Sky News for this month. As always, if you see any space news stories that you want me to explain in a future video, or if you snap any pictures of the night sky that you want to share, then tag me over on social media. I'd always love to see them. If you want more content like this, then don't forget that I co-host the Royal Astronomical Society's Supermassive podcast, so check that out. It's linked in the video description down below. And with Christmas coming up, just a little reminder that I do have some merch as well. There's JWST merch, there's Dr. Becky specific merch. If you have any family members or friends that are space obsessed, then it could be a very good Christmas present for them, or a nice treat for yourself as well. Until next time, everybody, happy stargazing. What are you doing now? Oh my gosh. No. Oh my gosh, no. Don't use the computer as a footrest. Through our solar system. Hello, meow. I think she's currently doing what we've dubbed Spider Cat, which is underneath the sofa and just The Very Bright Venus is... The Very Bright Venus? So that's not an official constellation. Oh, you're going to start scratching at the bottom of that thing again? Yeah, okay, bye. She is a menace, but I know you all love it when she's in the room with me when I film. Moving slowly but surely each night along their orbits. Baby, I put you on that side of the sofa so you wouldn't wobble the tripod. And she's playing with her own tail. Yep. In a year to use for observe. I have no idea what just happened. I malfunctioned. ESA, the European Space Agency. The only way that... Oh, I gotta want to show you where she curled up. Look, oh, my light's in the way. But look, she's there. Oh, hi, baby. I mean, look, she's just so pretty. Yes, I know. I'm beautiful. I'm beautiful, she says. Anyway,